Hello guys, welcome to this lecture, and in this lecture we will be seeing about recursion. We'll be starting to see about recursion. So we're going to see so much about recursion, and in this lecture I'll be giving you introduction about recursion. Okay, so just we'll start with the introduction to recursion. So if you take recursion, what are all the things that we are going to see in this video is we'll be seeing what is recursion, example of a recursion, and we will take an example and we will trace that recursion, how it is working. That is what tracing, how it works, line by line, how it works. Then stack is actually used in recursion. So I will explain you how stack is used. The stack memory part is used for recursion. So we will also see how that stack part is used. Then coming to time complexity, if you see, here I'll tell you how to find the time complexity of a recursion, and also about recurrence relation. If you have no idea about all these things, we will I'm going to teach you everything one by one. Okay, fine. So before starting to see what is recursion, generally we have already seen about what is function, right? So using function only we are going to proceed with recursion. So what is recursion means? Calling a function inside a function, inside the same function. Okay, it's inside the same function. So calling a function inside the same function in the definition of the same function. Okay, in the definition of the same function, inside the definition of the same function is what called as recursion. So you know how to write a function. You know that a function will have two parts. One is definition, the other one is calling part. So what I'm telling is that taking definition part and calling part, you know what is calling. So if the calling part is placed inside the definition of the function, then it is called as recursion. So calling a function inside the same function is what called as recursion. We will see in deep about exactly what recursion, what is the capability of recursion, what job it can do, everything we will see. But this recursion is one main important part of algorithms and data structure also. So when you want to get into data structure or algorithms, definitely you need to have a very good knowledge of how recursion exactly works. Okay, fine. So before starting, I'll just give you a general structure of how a recursion has to be. First of all, a recursion means it's a function. So first of all, you have to have the type of the function, return type of the function. We have already seen about all this return type. What is the return type of a function? All these things we have seen in the basic version that I have covered in the YouTube channel. Okay, so now here we have to first of all have a type, and then followed by the name of the function. So function name, then followed by parameters. Okay, followed by parameters, and then inside the body part we have to write a if condition. Why this if condition is? Because recursion means calling the same function inside the definition of the same function. So we are repeatedly calling it. So we are doing repetition of process. So already we know one repetition of process. What is loop? We will also see the difference between what is loop and what is recursion, because both are going to do the repeated process. So what is going to be the difference? Those things we will see in this video. Okay, so if repeated process is happening, then definitely you should have a termination point where the process should stop. For example, if you're writing a for loop, you will have a condition part to just verify where the loop should end. Suppose if you're not giving any condition, what will happen? The loop will start running for infinite times. Okay, so here also, since recursion is also a repeated process, you should have a stopping point. To specify that stopping point only, we are writing this if condition. But here in the general format, this if condition is for the continuity. See, if this condition which we are providing, if it is true, then the recursion will continue. The condition that we are going to provide, if it is false, the condition is false, then the recursion will stop. So we will be having a base condition where to stop and where to continue your recursion calls. So this is if condition, and inside this you can have any lines, any number of lines, but let me take that you can have any number of lines, and somewhere in between you will be calling the same function. You will be calling the same function again with the respective parameters. You'll be again calling the same function inside the definition itself. Okay, then followed by any other lines of code you might work with. So this is the general format of any recursion. First of all, you have to write a return type coming with function name, coming with parameters, then with the if condition, which will tell you that which will have a base condition, and this base condition, some condition you can provide, and if that condition is true, then this recursive call will keep on running. Suppose if the base condition is false, then it will stop the process. Suppose if base condition is not provided, what will happen? Infinite recursion will take place. So again and again the function will be called for infinite number of times, leading to overflow. We will also see what is overflow here. Stack overflow will happen, so we will also see about that. Okay, fine. So this is a general format of how to write a recursive code. Okay, so next one, we will be seeing an example of recursion. I'll be showing you an example of recursion, then you will understand it better. Okay, so now what I will be doing is I'll be taking a example of recursion. Okay, so example recursion. Example recursion. So let me just include stdio.h followed by main function. So now inside this main function, what I'm going to do, see, now I'll be writing a function with void return type. Void means nothing. Nothing is going to be returned. Okay, so void followed by fun, function called fun. We are going to take only one parameter called a, and I'll be writing if a is greater than 0, then you can process your recursion. So what you're going to do here, what I'm going to do is I'll be doing fun, again the same function I'll be calling, but with a different parameter called a minus 1. And after that I will be printing the value of a, so comma a. Okay, so hope this is the same format that I have given you already. Function name is first of all return type void, function name is fun, then comes a parameter integer a, then inside this you are having a if of base condition. So here also if of base condition is a greater than 0 is a base condition. So inside that what you can have any number of lines, but the same function has to be called again. So okay, you have also called the same function inside this condition with a different parameter. So this is the general format of writing a recursion. So I have taken recursion. So now in the main function, what I have to do is that I'm declaring a variable called n, and let me declare it to 3. And the next thing what I'll be doing is that I'll be calling the function by passing this parameter called n. Okay, so now I'll just show you the line by line process, what is happening here in this recursion, so that you might understand it in a very better way. So before that, I am here, I need to remember you a few things. I think I have already taught you about 3 parts in a memory block: heap, stack, and code section, which I have already taught you in the basic version. Okay, so if you see this is, let me take it as a heap. Okay, this is the yellow color that we have taken is going to be heap, and now I'm going to take this part as stack. So this is going to be stack, and followed by one more block, and this block is going to be acting like code section. you know all this. I have taught you all these sections before, all this segregations before itself. Okay, so now if you see, whenever you compile a program, what will happen whenever you compile a program? Whenever you compile a program, this main function is the entry point that I have already clarified. This is the entry point, entry gate. Okay, entry gate. So always you open the entry gate, then only you will enter a house. Similarly, you will open this entry gate, so you will start your execution from main function only. So whenever a function is executed, whenever a function is starting to execute, what will happen? I have told you something. There is something called as activation area, which will be created inside the stack for every function. So for this main function, one activation area will be see here, one activation area will be created here in the stack. For example, I can just show you. So one activation area like this. Okay, so one activation area will be created, and inside this activation area, what are all the variables that you require inside this function will be created there only. So how many variables you require in main function? Only one variable called n. So now what will happen here is a variable called n will be created here with 4 bytes. With 4 byte will be created here inside the activation area of main, inside the activation area of main. And what is the respective value here? The respective value is 3. So that 3 will be stored in the respective block. After storing 3, what you're doing actually, you are calling a function. You're calling a function, but still the complete line is not over. If complete fun of n, that function is over, then only all the lines of main function will be over. So once see, until you see the close curly braces of a function, the activation area cannot be deleted. The created activation area cannot be deleted until the last curly braces, closed curly braces of a function is executed. But still now the closed curly braces is not executed, because before that you have called a function called fun. So the flow from this line, from 13th line, the flow will directly go to second line. Okay, so second line, what it is? It is a new function. A new function is going to start executing. So what will happen? For this function, a new activation area will be created. Where it will be created? It will be created on top of the existing activation area. So we'll just create one more activation area here. So if you see one more activation area, I'm just I'm just creating one more activation area above the existing activation area. This new activation area can be called as fun activation area. Fun activation area. And what you're passing here, you're passing the value of n as a parameter. What is the value of n here in the main function? 3. So this 3 value is passed here to the argument. So a variable called a, see, whatever the parameter here, this parameter is created. A variable like memory block is created for it, and whatever you pass will be assigned to this variable. So you have created a new activation area. Inside this activation area, you will be creating a new block called a, and in that block called a, what will happen? The value that you passed from the main function 3 will be assigned to this a, whatever value that you are passing. Okay, so now what is the next thing? What is the next thing? What is it will check if a is greater than 0. So here if you see a is greater than 0, yes, it is greater than 0. So it will enter into this if condition. So it will come here to 6th line. After coming to 6th line, what is this line is telling? This line is calling one more function. It is the same function it is calling, but when it is calling one more function, what will happen? All the remaining lines will not be executed because a function is called. Suppose if you are calling one more function, what will happen? The execution will stop and the flow will be going to the other function. Am I right or wrong? Here also, coming to 13th line, you have called a function, so it did not entered into 14. It stopped here and the flow went here to the second line. Similarly, whenever you are calling a new function, what has to happen? Activation area has to be first of all created, and after creating activation area, the flow will be again given to the first line of the function. So since you are seeing one more function call, what has to happen? One more activation area has to be created. So what is the existing activation area? You have two activation area, which is main and fun, and this fun activation area has accepted 3 as a argument. Okay, fine. So now one more function is being called. Now just verify whether this call fun of 3, all the lines are executed. No, all the lines are not executed, because up to 6th line only we have executed. Still 7, 8, 9, 3 lines are remaining. So I cannot delete the existing activation area for fun. I will not be able to delete it because still few more lines have to be executed. But before executing these line, one more time the same function is again called. So what has to happen? The flow has to again be given to second line. At the same time, a new activation area will be created on top of the existing activation area. Okay, so I'll just show you that also. So if you see here, one more activation area will be created on top of the existing activation area. And this activation area, the new activation area which is created, what it will be having? Again, a variable called a will be created, and what you're passing in the call a minus 1. A minus 1. What is a here? 3. 3 minus 1, 2. So one more variable called a will be created in the activation area of the new fun activation area, and the new activation area is accepting 2 as the argument, because you are passing a minus 1 from this activation area. What is a here? 3. So 3 minus 1 means it will be passed as 2 here. So here also a is created and it is assigned with 2 actually. You can ask me how same variable name can be given. A same variable name can be given if those 2 variables are declared in a different activation area. I think these 2 variables are assigned in are created in a 2 different activation area. So in 2 different activation area, naming the variable with same variable name is possible. Okay, giving same name to the variable is possible when the variables are in the different activation area. So this is a different room and this is a different room. Both can have a same name. Okay, people with the same name. Both are different activation area. Okay, fine. Hope you understand why it is having the same name. Okay, fine. So now after this, what will happen? Then you will go and execute for fun of 2. For fun of 2, what you will check? If a is greater than 0. Yes, 2 is greater than 0. So then what you will do? Then fun of a minus 1. Again it is calling. So for fun of 2 also, 7, 8, 9 is not executed. See very carefully. For fun of 3 also, up to 6th line only I have executed. Still 7, 8, 9 is not done. For fun of 2 also, up to 6th line only we are coming. In the 6th line, I'm calling the same function again. So 7, 8, 9 is not executed. So if you call the same function again, what will happen? One more activation area will be created. I'll just show you. One more activation area will be created like this. And in this activation area, if you see, a block called a will be created. And what you're passing a minus 1. So 1 will be passed. So the new activation area is also fun, but accepting the parameter 1. Okay. Now what will happen? Again, it will be checking whether a is greater than 0. Yes, 1 is greater than 0. So again, 6th line, okay, stop. Again, I'm calling the same function again with a minus 1. So what will happen? It will stop. So for this also, 7, 8, 9 is not executed. So fun of 1 also, it is coming up to 6th line. 7, 8, 9 is not still. See, still the lines to be executed are 7, 8, 9. Here for fun of 2 also, still the line 7, 8, 9 is not so far executed. Here also, if you note down, here also 7, 8, 9 is not still executed. But before that, I'm calling the same function by passing a minus 1. So what is a here? 1. So 1 minus 1, 0. So first of all, one more activation area will be created for the new call. And in that activation area, so one more activation area I'm creating in the stack only. So on top of the existing activation area, and it is also going to have a variable called a block, and it is passing with a minus 1. So 1 minus 1 is equal to 0. Now again, what I will do? Again, I will just go and I will just check whether a is greater than 0. No, now the value of a has become 0. So 0 is not greater than 0. So the condition is false. So when the condition is false, I will not enter into 6, 7. So I will directly go to 8th line, curly braces completed, then comes to 9th line, close curly braces executed. So when I see the close curly braces of a function, what I told you, the respective activation area have to be deleted. So now I'm visiting the closed curly braces of this function. For which activation area? Actually for this topmost activation area only I'm seeing that closed curly braces. So what has to happen? So this activation area has to be deleted. This activation area have to be deleted. Okay, fine. Now what is the topmost activation area? A, which is having one value. This is the top. So I always, the topmost activation area will be the active activation area. So now A is having one in the topmost activation area. So how to delete this activation area? If this activation area have to be deleted, then all the lines have to be executed. Is it executed? All the lines are executed for this? No. Up to 6th line only it was executed. Still 7, 8, 9 is pending. So what you have to do for this activation area, 7, 8, 9th line, all the 3 lines has to be executed. So what is 7, 8, 9? 7, 8, 9 means 7th line is printing the value of A. What is the value of A now? The value of A is 1. So first of all, you print 1. Then 2 curly braces will be executed. So you come to 9th line. So when you come to 9th line, what will happen? Automatically the activation area have to be deleted. So now this topmost activation area will be deleted. So let me delete it. It will be deleted. Okay, fine. So now what is the topmost activation area? The topmost activation area is 1 of 2. Is all the lines is executed properly for this? No, still 7, 8, 9 is pending. So what is 7, 8, 9? Printing. So printing the value of A. What is the present value of A? 2. So the next thing that you will print is 2. So after finishing all these things, okay, over, deleted. Now what is the topmost activation area? 1 of 3. Is all the lines executed? No, still 7, 8, 9. What is 7, 8, 9? 8, 9 is curly braces, close curly braces, but 7 is printing the value of A. What is the present value of A? 3. So 3 has to be printed. Then after printing 3, then this activation area will be deleted. Fine. Now you come back again to the main activation. So the recursion call, everything is completely over. You have printed 1, 2, 3, and you have now returned back to main. All the lines is executed properly for main also. So what will happen? This activation area will also be deleted forever. So all the complete execution is over. This is what happens when a recursion call is being called. So that I will just show you here in the line by line process also. So whatever stack that I have shown you here, this is the same stack here. This is the same stack of the computer. Here everything will be shown. Whatever activation area being created, all this thing will be shown. So inside each and every activation area, whatever variables are there, that variables will be shown here in the variable section. So you have stack and variable. Stack here only the name of the activation area will be there. So when I click on a certain activation area, then whatever variables inside that activation area will be shown here. So shall we start? Yes. So I'm just starting the process from 10th line. Yes, that the process started. So if you see here, an activation area have been created here. This is what activation area called main. So if I click on this main, inside this main activation area, what is there? Only one block called n is there. It is having a garbage value called 0 now. If you execute line number 12, n is changed to 3. So n is now assigned with the 3. Now what you're doing, 13th line, a function call is there. So whenever you call a function, what has to happen? A new activation area has to be created on the top of existing activation area. So what is existing activation area? Main. So one more activation area for this fun function have to be created on top of this main activation area. So let me get into this call function. So can you able to see here? And above, on the upside of the existing activation area, new activation area is created for your fun. And now that activation area, what it is having? It is having A, and it is also having the value 3. Why? How? You have been passing the n value here. So that n value is 3. That 3 is passed to this variable called A. So a variable called A is created. So now if you click on main is having a variable called n with value 3. If you click on fun, now this activation area is having a block called A, which is having value 3. Now what you need to do, you have to check whether the present A is greater than 0. Yes, 3 is greater than 0. So I'll just execute. Okay, I enter into if block because the if condition was true. Now what is this? This is a new function call. So whenever you face a new function call, what has to happen? A new activation area has to be created. So when I get into this function, a new activation area is created. And inside this activation area, what it is, we are having a2. Can you able to see the same thing that I've explained to you in the Excel sheet? Yes. So now a value is equal to 2. So now what I have to do, I will be checking whether this if condition is true or not. So since this if condition is true, I will enter inside the block, and again I find a function call. What has to happen? The remaining lines will not be executed now since you see a function call. So what has to happen? Again, you will go to the first line of the function by creating one more activation area on top of the existing activation area. Please just watch here in this section. A new activation area will be created. Yes. Can you able to see now? Totally three activation area for fun and one activation area for main was created. Now in this last activation area, the a value becomes 1 because you are calling a minus 1, right? So it was initially 3 when you call, and then after you call again for a minus 1, it becomes a value become 3, and now a value have become 1. So now what will happen? 1 is still greater than 0. So this if condition is true. Again, sixth line, I'm seeing one more function call. Present a value is 1. So 1 minus 1, 0. So again, you call one more function, one more activation area is created. A block is created in that activation area also with a value called 0. Okay, now if you check a greater than 0, the condition is false. So I just come out of if condition, I come to last line. So last line of the function. In which activation area we are now? We are in the last activation area with topmost activation area, which is having a value 0. So now what has to happen? Since the last line is being executed for the function, then the topmost activation area have to be deleted. That's it. So I'm just executing 9th line, which will delete the topmost activation area. You can watch. Yes, activation area is deleted, and I entered the next activation area where the a value was 1. So now if you see, at last when I was calling this function, we were executing up to 6th line only. So now it entered into 7th line, because if I need to delete this activation area, then the remaining lines have to be executed. Then only I can delete it. So 7th line, what 7th line will have to do? It will have to print the present value of a, which means it will have to print 1. After printing 1, again 9th line is executed. What will happen? Again, if 9th line is executed, then the topmost activation area will be deleted, and you will enter into the next activation area where the a value is 2. We will check whether it is happening or not. Okay, so if I execute this line, our topmost activation area is deleted, and you entered into the activation area where a is equal to 2. Now what? For that activation area also, if I want to delete this, then all the remaining lines have to be executed. So 7, 8, 9. So 7th line a value is 2 now. So 2 will be printed now, and again 9th line executed. So what will happen? The topmost activation area will be deleted, and it enters into the next subsequent activation area. And now here also the remaining 3 lines 7, 8, 9 has to be executed in order to delete the current activation area. So what is the present value of a? 3. So 3 will be printed, and the activation area for fun is deleted. And if the activation area of the only one activation area is there, so if that is deleted, you will again go back to main function from where you came. So you will go back to 14th line because 13th line is completed. So when I execute this line, activation area for fun is deleted, and I come here to 14th line. And if I execute this 14th line, then all the activation area, everything is deleted, and complete execution is finished. Complete execution is finished. So if you see here, you can able to see there that it is printing 1, 2, 3. It is printing 1, 2, 3. Okay. So this is how a recursion generally works. This is how a recursion generally, works. Okay, so what we have seen so far is, we have seen what is generally recursion, and we have seen the basic structure of how recursion have to be written, and we have taken an example of recursion. And I have shown you how stack is used in the recursion. Is it stack, right? Whatever I showed you is what stack is all about. Why it is called a stack? Because you are creating the activation area one above the other. So the last created activation area is on the top of the stack. Last created activation area is on top. So when the last created activation area is on the top, only the topmost activation area is the active activation area. So if you want to delete the last activation area, only the topmost activation area only can be deleted. So last created activation area can be first deleted. So last in first out principle is being followed here in this memory block. That is why that memory block is called a stack memory block, as well as it is called as stack memory, as well as it is called as a concept called stack, because it is following a principle called first in last out, or otherwise last in first out. Okay, fine. So now we will be stopping this session. In the next session, I'll show you the tracing recursion using tree structure similar to stack. I'll show you about with a tree structure, and also I will teach you about how to find the time complexity of this example recursion that we have taken, and also we will see how to write a recurrence relation for the example recursion that we have taken here in this lecture. Okay, so this is it for this session. So we will be seeing in the next lecture. Thank you. Hello guys, welcome to this lecture. Uh, I think we have started with the recursion. Hello guys, welcome to this lecture. And in this lecture, we'll be continuing the session that we started in the last video with the recursion. Okay, so we'll be continuing with the recursion. So if you see in the previous lecture, we have discussed about what is recursion, and we have took one example of recursion here, one example of a recursion, and we also see how stack is used in this recursion, both manually also I showed you, and here in the compiler also by debugging it also I have shown you the line by line stack creation process. Okay, so now today what we will be doing is that I'll be showing you a tree recursion. Like I'll be showing the same recursion process using a tree. Okay, so we are going to trace a recursion, and after tracing it I'm going to show you how to find the time complexity of this particular recursive code. Okay, fine. So first of all, we'll just go into tracing recursion. For tracing recursion, see, I think this is the code for which we are going to trace it. Am I right? So this is the code for which we are going to trace. So we will just take okay, fine. So if you see here, for this code, we are going to draw a recursion, a tree. Okay, a recursion tree like structure. Okay, fine. So now what we will do is, first of all, we'll just take main node. Okay, so what this is going to point is that the function, you made a function call here in the main function. Your first function call is here in the main function, which is fun of n, where n refers to 3. So initially what call you made is that you called the function fun and you passed 3. This is a very initial call that you did. Am I right? So after calling f of fun of 3, you enter into this fun function and tell me how many lines are here. 6, 7 main lines. Okay, see, the main lines are 6 and 7 only. Operations are carried out in only 6 and 7. So two operation is carried out for fun function. Okay, so two operation will be carried out for fun function. So what I will do is I'll draw two. Let me draw a two process. Okay, two sub process which will happen for this fun function. Okay, so I'll just take one more function also. Okay, fine. So now two operation will be happening for this fun of 3, and one on the left, one I'll take that as a left process, first process, and another one is a second process. Okay, so I'll just take one more shape, place it. So you have called fun of 3. Now that fun of 3 is having two lines to be executed. One is fun of a minus 1, the other one is printing the value of a. So which is so first of all, before that you have to check whether a is greater than 0. Here a is 3, a is greater than 0. So these two process has to take place. These two process has to take place. So what is the very first process? The very first process is calling the same function fun, but passing a different argument called a minus 1, reduced value. of a. So what is the current value of a? 3. What will be the reduced value? The reduced value will be 2. Okay, fun of 2. What is the one more process? Printing the value of a, which this will not happen now. This will not happen now because you have called a recursive function. It means that you have called the same function again. So this seventh line will not execute. Since this line is calling the function itself, it will move its scope to the first level. It moves its control to the first line of the function. So this printing statement will not execute now. We will stop it here. We'll hold. We will now go to this fun of 2. So you will again start from first line. Is a is greater than 0? Yes, 2 is greater than 0. So what has to happen when a is greater than 0? These two lines have to be initiated. So for fun of 2 also, two things have to be executed. So take two more nodes. Okay, let us take two more nodes, for example. So let me just make it small, okay, for you to see it clearly. See, let me reduce the size of each and every node so that you will be able to easily see it in the same page, single page itself. Okay, fine. So what I will do is I'll just take it here. Okay, fine. So now if you see, these two are the nodes for fun of 2 actually. So one is the left side call, first call. The first operation. The second one is this node is for second operation. So this is for recursion call, this is for printing. So always the left node is for the recursion call, right side node is for the printing call. Only printing statement for this function only I'm saying, for this recursion. So fun of 2, again when you call fun of a minus 1, what will happen? It will be calling fun of 1. It will, because you have called the same function again, so the flow will again go to second line. So this seventh line will not be executed for now. This line will not be executed for now. Okay, so now what will happen? This printing statement will not be executed now. Instead of that, this fun of 1 will be having two new process. Okay, it will be having its own new to process. Okay, so now taking this process in hand, okay, taking these two process, if you see, what is the left process we have? What is the left process? Recursion call. What is the right process? Printing the value of a. So coming to this left side, it is again calling fun of a minus 1, where a is 1. So a minus 1 means fun of 0. So you are initiating fun of 0. Now tell me whether this call will happen. No, this printing statement will not happen now. So now what I will be checking is, what I have to check is, I will be again going to the first line of this fun of 0. See, because you have called a new function, I'll again go to this second line. I will again start with fourth line, whether a is greater. No, a is not greater than 0. So when a is not greater than 0, then these lines have not to be executed. So suddenly you move out of if condition, you come to ninth line and you execute ninth line. So ninth line means it is the last line of this function. Of which function call? For fun of 0. So what has to happen actually? So this, because no more recursive call is there. No more recursive call, because this is completely a false condition. So no more recursive call. So your recursive call has stopped. So no more call here. So the work of this is over. The work of this is over, completed. Okay, the work of this is completed. Now coming here, so when the work of this is completed, what will happen? So you consider the same structure using that stack. In stack, how I showed you, the stack will be created with activation area one above the other. So for fun of 3, 1 activation area, fun of 2, 1 activation area, fun of 1 activation area, fun of 0 activation area. So this is a topmost activation area. Fun of 0 is the topmost activations area. So when all the lines are executed for a particular function, what has to happen? Corresponding activation area have to be deleted. So what will happen? The activation area of fun of 0 will be deleted, and you will go back to the previous activation area, which is fun of 1. So coming to fun of 1 had two process, whereas you have finished one process, but still one more process is pending. What is that process? Printing a is still pending. Okay, so what I need to print? I need to print the value of a. What is the value of a here in fun of 1? The value is 1, so you need to print 1. You need to print 1. Okay, so I think both the work is finished for fun of 1, so all the work is done for fun of 1, so that this activation area also will be deleted. And after deleting this activation area, you will go back to the previous activation area. And coming back to this activation area, only one process is so far over. One more process is pending, which is printing the value of a. What is the value of a here? Value of a is 2, so you have to print 2. So two works, both the works have been finished for fun of 2, so delete this activation area. This activation area will be deleted, and you will go back to fun of 3, the previous activation area. Coming to this activation area, only one process is over. One more process is printing the value of a, where the value of a is here 3, so print 3. Print 3. Okay, after printing 3, both the works for fun of 3 is over, so completely this fun of 3 activation area also will be deleted. So you know, the overall recursion tree is completely deleted. So what we did initially, we called fun of 3 in the main function. Then what we did is, since I find a recursive call fun of a minus 1, I called fun of 2. Then fun of 2, I again called the same function by a minus 1, so fun of 1. Again I called the same function with a minus 1, so again came to fun of 0, where a is now equal to 0, which means this condition, base condition, is false. When base condition is false, the recursion is going to stop. So no more recursion will take place after the base condition becomes false. Then what I will do, I will go back to the previous activation area, and I will finish the one more pending job, which is printing the value of a. Similarly, I will go for the previous activation area, do that second job, go to previous activation area, do the second job. So in which order you will be printing it? You will be printing it like 1, 2 and 3. So this is how you represent a given recursion as a tree. So I'll show you for even the complex recursive structure also. I'll just show you this recursion tree. Okay, so this is a very basic structure for this example recursion that we have taken. So using this tree, what I wanted to tell you is that, okay, I'll just show you one more thing. Okay, I'll just show you one more thing. See here, I think, hope you have observed what happened in this recursive tree. Yesterday itself, I have taught you something using Excel sheets. I have shown you the main memory actually. So again, here also one main memory. I'll take a main memory. I'll just split this main memory into 3 parts. One is heap. This is a heap section. And one more part is going to be code section. So this is code section. This top surface is going to be heap, and this middle surface is going to be heap memory. It's going to be heap memory. Okay, so what has to happen? For example, if you are taking 1 minute. Okay. One minute. Okay, fine. So if you see here in this function, if you see here, I told you every time the main function will be the starting point of the program, and whenever a main function is invoked, I told you corresponding activation area will be created for it. So initially one activation area will be created, and this activation area is actually for the function called main. Okay, so this is actually for the function called main actually. Okay, fine. So it's very difficult to write for me, so just adjust for me. Okay, so now this is a activation area which I have created for main function, and inside this activation area, what will happen? Whatever the variable which is required inside this block will be created here. It will be created here. So what is the activation? So you will be creating a block. You'll be creating a block, and this block is for actually n. This block is given the name called n. And what will happen, you have stored 3 in that variable, so automatically what will happen, a value called 3 will be, okay, a value called 3, okay, just you understand that I'm just writing 3, okay. So value called 3 will be stored here in this block. And after doing that, what is happening, one more function called fun is called with the argument, by passing the argument called 3. So what will happen, one more activation area will be created on top of the existing activation area, okay. It will be created, 1 minute. One more activation area will be created on top of the existing activation area. And what for this activation area is for, this activation area is for the function fun. This activation area is for fun with the argument, by passing the argument called 3, by passing the argument called 3. So now in this activation area, what will happen, you are passing the value of n to this a, so automatically 3, this n value 3 will be passed to a. So first of all, in this activation area, a variable called a will be created, and then it will receive this value 3 which you are passing. So what will happen here, one block will be created, and that block is referred by the variable called a, and this will be storing the value called 3 because you are passing 3. Since you are passing 3, this block also will be storing the value 3. Okay, now what will happen, it will go and check whether if a is greater than 0. If a is greater than 0, what will happen, it is again calling the same function. So when it is calling one more function, what will happen, one more activation area have to be created on top of the existing activation area, and this activation area is also for the function fun. Okay, this is also for fun, but with a different parameter. It is a minus 1, which is 3 minus 1, which is having 2 actually, okay, which is having 2. So here actually the parameter is 2, but this is also for the same function fun. So here what will happen, here one more activation area will be created, and that activation area is given the name called a. This is given the name called a, and what will be stored here, 1 less than this 3, reduced value of 3 will be passed here, so it will be storing 2. It will be storing 2. So after doing this, what will happen, again you will start checking whether the current a is greater than 0. Yes, 2 is greater than 0. So I will again go to the 6th line. I will be again calling this function. So one more activation area will be created. One more activation area will be created on top of this activation area. So inside this activation area, one block will be created. That block will be named, okay, that block will be named with a variable called a. Okay, so this is completely, this block is given the name called a. Okay, this block is given the name called a. And what will happen, what value will be stored here, the value 1 will be stored because you are calling a minus 1. So here 2, so 2 minus 1, 1 will be stored here. Then after doing this, what will happen, again this current a will be checked whether it is greater than 0. Yes, 1 is greater than 0. So what has to happen, one more activation area will be created on top of the existing activation area, and inside that one block will be created, and this block will be given the name, this block will be given the name called a. And what is the value which will be stored here inside, what is the value stored here inside, 1 minus 1 equal to 0. So here the block will be stored with 0. Now again what will you will check the current value is greater than 0. No, the current value is 0, which is not greater than 0, so nothing will be executed. So you will reach the last line of the function, so complete line of execution will be over for this fun which is having the value 0. So what has to happen, the activation area have to be deleted. Okay, this activation area have to be deleted. After deleting this activation, so this is the first deleted activation area, so deleted, I'll also tell you the number, this is first deleted. So once this activation area is deleted, your control will move to this next activation area, the next top activation area, which is having the value 1. So if you come to this activation area, I think at last what we have done is we have reached up to only this fun of a minus 1. We have not still executed the 7th line, which is print. F. For none of this activation area we have executed this 7th line, so we will execute it now. So what we will be doing, we will be printing the value of a, which is 1, and we will delete, and we will be deleted, we will be deleting this activation area. Okay, we'll be deleting this activation area. So this is deleted actually second. This activation area is deleted first, then it is second, it is deleted, this activation area is deleted. So once this activation area is deleted, then you will move to this activation area, and this activation area, one more job, printing job is printing. So you will be printing that a value, which is 2, and you will be deleting this activation area, you will be deleting this activation area. And this is next, third, first deleted activation, second deleted activation area, third deleted activation area. So after finishing this, I will enter into the next activation area, and I'll be printing 3, and after printing 3, I'll be deleting this activation area. So this is deleted for the fourth deleted activation area. Then after deleting this, I will enter into main function, where main function also all the job is over, so I will not do any more work, I will be deleting this also. So this is deleted at last, this is deleted at last, so this is deleted for fifth try. Okay, fine. So now if you see, I just see two phases here. One is creation of activation area. On the one phase, you are creating activation area. On the other side, you are deleting activation area one after the other. So creation of activation area and deletion of activation area. So what I will just tell you is, 1 minute. So what I will tell you is that initially there are two phases in a recursion process. Two phases in a recursion concept. Okay, so what are they? What are the two phases? One is actually creation of stack, creation of activation area. What is the second one? Second one is deletion of activation area. So this creation of activation area is also called as calling phase. This is also called as calling phase. And this deletion is called as actually returning phase. Okay, this calling phase is having one more name called as ascending phase. And this returning phase is also having one more name, which is called as descending phase. Okay, fine. So which is actually the ascending phase? If you see here, fun of 3, fun of 2, fun of 1, fun of 0, these are all ascending phase, because these are all creation of activation area. Then which is deletion of activation area? Deletion, on deleting only, what you did, you printed 1. So this 1, 2, 3, printing all these things are actually returning phase, descending phase. So fun of 3, fun of 2, fun of 1, fun of 0 are all ascending phase, and this 1, 2, 3, printing 1, 2, 3 is what called as descending phase. Descending, because while you're coming from top to bottom, you call this function. When you go from bottom to top, you are printing 1. So top to bottom is creation of activation area, bottom to top. Here in the recursion tree only I'm saying, not in the stack. In the tree I'm saying that from top to bottom is called as ascending phase. From bottom to top, if you are moving, then it is called as descending phase. I think this fun of 3, fun of 2, fun of 1, fun of 0, you are moving in the forward direction from upside to downside. But here this 1, 2, 3, from bottom to top only we were doing. Okay, we were not initially printing 3, then printing 2, printing 1. We were initially printing 1, then followed by 2, followed by 3. So this is called as descending phase, and this is called as ascending phase. Okay, one more thing that I wanted to tell you. You can observe here in the diagram also, here in this tree also, you can observe one thing, that whatever lines that you are writing before recursion call, see, you can divide this into two parts. Okay, you can divide this into two parts. before recursive call, before recursive call, and one more thing is after recursive call, after recursive call. So before recursive call, whatever you have written, whatever lines of code you have written, those lines of code will be executed in the ascending phase itself. It will be executed in the ascending phase itself. How? Because all these lines are on the top of recursive call. So whenever you call this function, all those lines which is above this recursive call will be executed, and then only this will be called. So this is going to be this will be executed at the time of creation of activation area itself. Whatever the lines that you have written on before this recursive call, those lines will be executed. Those lines will be executed at the time of creation of activation area. So I'm telling that whatever lines that you're writing before recursive call will be carried out, will be executed in the ascending phase. So whatever lines that you're writing after the recursion call, which will be executed in the descending phase, which will be executed in the descending phase, which will be executed in the descending phase. Yes. Yes. So in this video, what we have seen so far is we have started by seeing the tracing of recursion using tree, and also I have again showed you how it is created in the stack. So creation of activation area is happening, deletion of activation area is happening. So using that, we said that there are two phases in a recursion concept. One is creation of activation area, which can be also called as calling phase, which can be also called as ascending phase. Then comes the deletion of activation area, which can be called as returning phase, which is also having one more name called as descending phase. Okay, fine. So now we will be entering into the fifth part of the session, which is time complexity, finding time complexity. Okay, so shall we move to that? Actually, we'll move to that, finding the time complexity. So how to find the time complexity? There are two ways to find time complexity for a recursive code. Okay, for a recursive code, there are two ways of writing a for finding a time complexity. One is the manual way that we have already seen. One more way is the recurrence relations. First of all, we will finish the manual method and then we will go to recurrence relation. Okay, fine. So coming here to this line, so taking a variable called n and storing 3, what this will take? This will take 1 unit of time. This will take 1 unit of time. Then what about this fun of n? Fun of n, I'll just go here and we will just I'll just execute here. How much time this has to execute? So coming to if condition, how much time this if condition will be executed? You're calling this function again and again. Okay, you're calling this function again and again. So this will not be executed for only one time. This will be executed for multiple number of times. We will find how much time. You can take this tree structure. How much time function have been called? 1, 2, 3, 4. These three things are successful recursive call, and this is called as unsuccessful recursive call because this failed. This is a fail condition. A equal to 0 is a fail. But even though it is a fail condition, definitely this condition could have been checked. So how many recursive call? 4 recursive call. How we can generalize? So if you call fun of 3, then 4 recursive call. If you call fun of 4, then 5 recursive call. So you can generally say that if you pass n, you'll be getting n plus 1 recursive call, n plus 1 recursive call. Okay, so there will be totally n plus 1 recursive call only for this recursion. Only for this recursion, there will be totally n plus 1 recursive call. From the tree diagram, we were able to confirm it. Okay, so there are totally n plus 1 recursive call available. So if n plus 1 recursive call is happening, then how much time this if could have happened? If could have checked. This if could have been checked for n plus 1 time, because n plus 1 recursive call is happening. So n plus 1 times you could have recursively called it. So totally n plus 1 time executed means n plus 1 unit of time will be taking. This statement will be taking n plus 1 unit of time. Then coming inside, how much time this function call has been done? N plus 1 time. So this function recursive call also could have taken n plus 1 unit of time. Then coming here to the printf statement. This is executed for how much time? That also you can find here in the recursive tree. only 3 times only we are printing. What is the 3? 3 is equal to n value here. Okay, n value. So 3 times only this printing statement is taking place, which means that n time. So if your n value is 3, this printf statement will execute for 3 times. If this n value is 10, then this will be taking this will be executed for 10 times. So generally I'm telling that this is going to be executed for n unit of time. So how will I get the overall time complexity? We have to add all this. So I have to add this n plus 1 plus n plus 1 plus n. So totally this is equal to 3n plus 2. 3n plus 2. So you can say that this is going to be equal to 3n plus 2. So what is the overall time complexity of the entire program? You can add both this time complexity, so which is 3n plus 2 plus 1, which is equal to 3n plus 3. So taking this equation 3n plus 3, what is the highest degree here? The highest degree is 1. Highest degree is 1. So if the highest degree is 1, what can be the corresponding time complexity? Order of, you have to take only the term which is having the highest degree, which is n. So I'm going to tell that this is only order of n. So the time complexity of this recursive code is order of n. But if you see here, since here this recursive call is very easy call. Okay, this is the very easiest call. Easy recursion, very simple recursion that we are doing. So when this is a very simple recursion, then using the tree diagram, we will be able to know how much time this is recursive call is happening, how much time printing statement is executing. So we were able to figure it out. But if this is a very complex recursive function, if this is a very complex recursive call is happening here, then how you find the how you find the time complexity? So when you have a very tough or very complex recursive call in place, then only you enter into a concept called recurrence relation. You enter into a concept called recurrence relation. So what you're going to do here in recurrence relation, I'll just tell you. Okay, so before that, I'll just simply take all these things. I hope you have understood how this is order of n. Okay, so again, now what I will do is I'll just take all these things off, sorry, and we will go for recurrence relation. So coming to recurrence relation, if you see, I think in mathematics you could have learned this recurrence relation somewhere, but I think you don't understand the importance of recurrence relation, which you will understand in the upcoming classes that I'm going to show. See, recurrence relation is a very, very, very important concept. Without recurrence relation, you cannot enter into the testing of algorithm. Okay, so the testing of many algorithms like backtracking algorithms, dynamic programming algorithms, many more algorithms, greedy algorithms, which we have, divide and conquer, all this algorithm testing is done in recurrence relations. Very major, very important concept that you should learn, because when you want to test the efficiency of a program where recursion is taking place, then definitely recurrence relation is the one concept that will help you. Without knowing recurrence relation, you cannot find the, you will not be able to find the exact time complexity taken by your code, by your recursive code. Okay, fine. So what I have to take is that we are having a function, recursive function. This recursive function I can generally take it as, okay, this recursion function can be generally taken as t of n. Let me take, because function of some variable, right? So t of n is generally I'm taking it as t of n. Now, how much unit of time will be taken by if condition if it is executed for only one time? In the manual case, we were finding how much time if condition was executed, but now we are not going to find how much time if is executed. We will say that this statement will be taking 1 unit of time if this is executed for one time. I'm just telling that this statement will be taking 1 unit of time if this is executed for one time. Then coming to this one, if fun of a is taken as t of n, then fun of a minus 1 should be taken as t of n minus 1. Am I right or wrong? If fun of a is taken as t of n, then fun of a minus 1 has to be taken as t of n minus 1. So this is taken as t of n minus 1. Then coming to printf statement, how much time this printf statement, one time if this is executed, then 1 unit of time. So coming to recurrence relation, you should not find how much time each and every line is going to execute. Okay, you are going to generalize the function that you're writing. So if you now add this, what you will be getting, if you add all these things, so you can first of all write t of n is equal to, okay, I'll just write t of n is equal to t of n minus 1 plus 1 unit here, 1 unit here. So totally it is equal to 2 unit. If your n value is greater than 0, then this recurrence relation will work. Suppose if my n value is equal to 0, if n value is equal to 0, what will happen? If my n means that a value, if a value is becoming 0, if this a value becomes 0, what will happen? These two lines will not be executed. These two lines will not be executed if your n value becomes 0. So you cannot say that it is t of n minus 1 plus 2. If a becomes 0, only this if your n value becomes 0, then these two lines will not be executed. So only this if condition will be executing. So if your n value is 0, only 1 unit of time. So your t of n, okay, t of n will be equal to 1 if your n value is 0. Why? Because if your n becomes 0, then these t of n minus 1 and 1 unit, these two lines will not be executed. So you should not include this unit of time when your n is equal to 0. So now we have taken the recurrence formula. This is generalizing a given recursive function into a formula. Okay, we have written this like a formula now. We have written the given recursive condition have been converted to a formula like this. Now what we should do? We need to solve this recurrence equation. We have to solve the recurrence equation that we have taken so far. How to solve this? We are having two methods to solve it. One method is by induction. The other method is by successive substitution. Successive substitution method. Okay, now what we are going to do is we are going to choose successive substitution method. What is the first step that we will do in successive substitution? Okay, what I am going to do is that first of all I'll take the initial equation. What is the initial equation? Initial equation is t of n is equal to t of n minus 1 plus 2. See, always whenever a constant value like 2, 3, 4, 5 is there, while we are solving that recurrence relation, we have to convert it into 1. Whenever you have a constant value like 2 or 5 or 10 or 15, you have to convert that into 1. You have to convert that into 1 while you are solving it. Not while representing it, while you are solving it. Okay. So this is the equation. T of n is equal to t of n minus 1 plus 1. Then what I'm telling is that if t of n can be expanded to t of n minus 1 plus 1, then why can't we expand t of n minus 1? Yes. So if you expand t of n minus 1, what will happen? That I'll show you. If t of n minus 1 is expanded, this can be expanded to t of n minus 2 plus 1. T of n minus 2 plus 1. Is it right? Is this right? Yes. Because you are taking n minus 1 as a single term. Okay, as see, if t of 3 is equal to t of 2 plus, so I'll just show you one example. If t of 3 is equal to, t of 3 is equal to t of 2 plus 1, that is what this equation is telling. Am I right? T of 3 is t of 3, 2, 3 of 3, t of n is equal to t of 3. Equal to t of n minus 1 means t of 2 plus 1. When t of 3 is written as t of 2 plus 1, then why can't we rewrite t of 2 equal to t of 1 plus 1? T of 2 can be rewritten as t of 1 plus 1. Am I right? That is what we have done here. Okay, so this thing can be read. See, instead of t of n minus 1, you are writing this as t of n minus 2 plus 1, and extra you are having one more 1. So when you add it, you will be getting 2. So this equation, if you see, this equation is equal to t of n is equal to t of n minus 2, because instead of t of n minus 1 you are substituting t of n minus 2, so this becomes t of n minus 2 plus this one plus this extra one. This one plus this extra one both will give you 2, so this is equal to 2. So t of n is equal to t of n minus 2 plus 2. Now again expand t of n minus 2. Again expand t of n minus 2. So when you expand t of n minus 2, what will happen? T of n minus 2 is equal to t of n minus 3 plus 1. When t of 1 is expanded to t of n minus 2 plus 1, then t of n minus 2 is expanded to t of n minus 3 plus 1. So how we can rewrite this formula? Now you can write this as t of n is equal to t of n minus 3 plus in this formula you have 1 and here 2, so both together you will be getting 3. So in this manner you can keep on extending this function and keep on going. So successive substitution, we are doing successive substitution here. So now up to when this expanding will go? Up to when my n is equal to 0. Until my n is equal to 0, this expanding will keep on going. When my n will be equal to 0, this entire term. So first of all I will generalize this equation. So t of n is equal to t of n minus k plus k. What is this n minus k? See, 3 I am generally taking it as k. This 3, 2, 1 I'm just generally taking it as k. So if this 1, 2, 3 is taken as k, here if you see, if this is 1, this term is also 1. If this term is 2, this term is also 2. If this term is 3, this term is also 3. So if this term is k, this term also will be the same k. So I'm generalizing this. Okay, I'm just generalizing. So now tell me when this process will stop. When t of 0, at t of 0, because when your n becomes 0, the process will stop. So when this entire term so if you see here, this entire term n minus k has to become, because at t of 0 your process stops. So if this entire part becomes 0, then it becomes t of 0 and the process stops. So what has to become 0? N minus k has to become 0. If n minus k is equal to 0, can we rewrite this? Because this subtracted by k will go to the right side in addition, with addition symbol. The symbol will be changed. So can we rewrite this as in equal to n equal to k? N minus k equal to 0 can be rewritten as n equal to k. Okay, so when n is equal to k, now I will start substituting n instead of k. So what this will be converted to? So t of n is equal to t of n minus n, because both are same, right? So instead of k, let me take it as n. So n minus k, so can be rewritten as n minus n, then plus instead of this k also, let me take it as n. Now how this is rewritten? T of n is equal to, what is t of n minus n? This is t of 0 plus n. What is t of 0? If n becomes 0, t of 0 will be equal to 1. That is what we have written in the equation itself, representation itself. So how we can rewrite this into? This can be rewritten as t of n is equal to 1 plus n. So this is a final answer. This is a final equation, polynomial equation. We get a polynomial equation like 3n plus 2, like that, right? So similar to that, we are getting 1 plus n. So what is the highest degree of this equation? The same process. After the same process, so the highest degree is actually 1. Highest degree of this polynomial equation is 1. So what I have to do, I have to take only that highest degree part alone. So this can be rewritten as order of n. The same we also found previous step also, we found the same time complexity, but now using this recurrence relation, using successive substitution method, we are finding. Don't ask me for every recurrence relation will a successive substitution help. No. Okay, so in the upcoming session, what we will be placing is that I'll be placing three special sessions for exclusively recurrence relation. There we will be seeing many recurrence relation like T of n minus 1 plus 2, T of n equal to T of n minus plus 2 relation, and I'll show you for each and everything. So that if any recurrence relation after this if any recursion program that we are writing, that recursion program will fall into any one of the recurrence relation that we will be seeing in the three sessions. Okay, so whatever recursion program that we will be seeing in the further course, those recursion will definitely fall into any one of the recurrence relation that we will be solving in the upcoming three special videos, three.
Hello guys, we have posted your attendance link in your chat section, so kindly give your attendance. This will be open only for 5 minutes. Okay, so give your attendance before that. Thank you guys. Guys, kindly give your attendance. We have posted your attendance in your chat section. Okay, it will be active only for 5 minutes. Okay, so kindly give your attendance before that. Yeah, thank you.
three special sessions that we will be seeing on recurrence relation. Okay, so we have discussed very deeply about time complexity of a recursive code, and now we have not so far seen about the space complexity. What will be the space complexity? Okay, we will see that. Okay, we will see that. Okay, I'll just show you the line by line process to make you understand how much space this is taking place. Okay, so we will just start the process here from the main function. Yes, the program started its execution from main function. So one activation area for main is created inside your stack, and inside that main activation area you're having a variable called n with 0. Now initialize your n with 3. After that you can call this fun by passing this argument 3. So one more activation area, this on all already I have shown you. One activation area will be created for this fun with argument 3. So one more block for one more variable a, one more block is created here with value 3. And now I'll be checking whether if a is greater than 0. So condition is true, I will enter. Again one more function call, so one more activation area will be created where that activation area will be having one more extra variable, extra memory block for a with value 2. And now again checking a greater than 0, yes true, I will enter inside. I will make one more call, so one more activation area will be created, one more block will be allocated with the value assigned with value 1. Again if condition is checked true, again the function will be called, again one more activation area will be created with again one more block with value 0. Now your condition becomes false. See, now at this point I will stop because the creation of stack is over. While I'm creating the stack, how many variables we are having? Shall we make a count? Here in the topmost activation area I'm having a variable called a, so one variable. In the second activation area I'm having, from the top side, the second activation area, that is one more variable called a with value 1. So these are two different variables. You don't think that these are two different variables having two different memory blocks. So one variable in the next activation area, second variable, next activation area, third variable, next activation area, fourth variable, and finally one more main function we are having fifth variable. So how many variable? 5. So 5 variable mean how we can say for every whatever the input of n, whether it will be creating 5 variable? No. If fun still your n value, since your n value is 3, you have created 4 activation area. That already we have seen that if your n value is 3, totally n plus 1 recursive call. So for every recursive call, one variable is extra created. So how much space, how many variables will be created for this recursion call? N plus 1 variable will be created because for each and every activation area, one variable. How much activation area? N plus 1 activation area. So how much unit of space? N plus 1 unit of space for your function, n plus 1 unit of space for your recursion function, for your main function one more variable. So totally n plus 1 unit of space. So n plus 1, 2 unit of, so when the equation is n plus 2, what is the highest degree? 1. What is the part? N. So this can be rewritten as the space complexity can be said here as order of n is the space complexity. Okay, so now I think we also in the introduction video also what I have told you is that recursion is also repetition of process. Same process is again and again repeated for some number of time. Loop is also repetition of process. Loop will also repeat the same process again and again for a repeated number of time. Now what is the difference between a recursion and a loop? Because both are repetition of process, so we need to understand what is the difference between the difference between a loop and a recursion. Yes, the difference is recursion is having two phases like ascending phase and descending phase, calling phase and returning phase. You follow a path and you return back in the same path again. So you go forward and you come backward. But coming to a loop, you can go only forward. You cannot come back in the same path where you traveled. Okay, you can start from a place and you can end at a place. You cannot travel back to the same places that you have already traveled. You cannot travel back to the same places. So this is what the main difference between recursion and loop. So loop can be only a loop is having only calling phase, but recursion is having two phases. One is calling phase and returning phase. And loop will not create any any activation area like this. Since activation area like this is created, your stack is consuming more memory comparing your for loop. So recursion will consume more memory comparing your loop. Okay, right? So we will also have a separate session for the comparison between loop and recursion. In which places loop will be efficient, in which places recursion will be efficient, will be help you. Okay, will help you. Okay, fine. So in this video, what we have done so far is, let me complete this. So in this session, in the previous introduction to recursion, we started with what is recursion. Then we took an example of recursion using stack we saw in the previous lecture. Today's lecture we started with the recursive tree, and as well as I have also shown you again how it works in stack. And then we started the concept of how to find the time complexity. And now we are entering into how to write a recurrence relation. How to write a recurrence relation to find the time complexity of a given recursive code. Okay, fine. So this is it for this session. So in the next lecture, we will be starting with types of recursion, and we will move forward with recurrence relation and the type of recursion, and we will see many problems related to recursion. So recursion alone will be taking nearly 10 to 12 parts separately. Okay, so very briefly we will be seeing about recursion, complex concepts about recursion, all those things we will be seeing. So far we have completed only the basics of recursion. Hereafter only the game is going to start. We are going to see many tough concepts inside recursion. Okay, so please be ready for the roller coaster ride. Okay, so thank you. This is it for this session. Thank you.